Hi everyone, this video explains the concept of strain energy, which is part of the materials topic for A-level physics. We will also look at the behaviour of polymeric materials. If you want to get the free worksheet for this topic, along with lots of other resources, then click on the link in the description. Enjoy the video. Hi there, this is Materials Lesson 2. So materials is a much shorter topic compared to electricity and waves and mechanics. And for most specifications, strain energy and polymeric materials is all the extra stuff you need to know in addition to Lesson 1. Right, so strain energy, this is a fairly straightforward concept. So we've already seen the force extension graph. You will have plotted this as a practical at GCSE and probably as a core practical at A-level. So we have our straight line elastic section, and then we have the elastic limit, and then a curved section, which is our plastic section. And we know that the gradient F over X is the spring constant, also known as the force constant. But this is also true. The area underneath the graph represents the work done. That's really, really important. And the reason why is because W equals F times D. So this is a really useful formula which crops up all the way through the physics course. So F times D, force times distance or extension, that is what we're finding here. So the area represents the work done, or indeed the energy and strain energy. So if I'm trying to find the work done of this section here, the elastic section, it's not a rectangle, it's a triangle. So it's half times base times height. So we end up with this formula, half Fx. So be careful, it's very similar to F times D, but we divide by 2 because it's a triangle. So that's our general formula of strain energy or work done. And we have a second version because I know that F is equal to Kx. We know that from lesson 1. So if I substitute that into this formula, I end up with half Kx squared. So we have two formulae which we can use depending on the information that we're given. So this little paragraph here is really important. If you imagine getting a rubber band and pulling it and then releasing it, it will fly away. So we've converted elastic potential energy into kinetic energy and maybe a little bit of heat. So if we strain something elastically, that means within the elastic region, then the energy will be recovered, or the vast majority of it will be, when the material is released. And that is why we have this conversion from elastic potential energy into kinetic energy when the elastic band flies across the room. But if we bend it backwards and forwards and end up changing the shape, so if you imagine getting an old credit card, not a current one, or something like a little piece of metal like a paper clip, if you bend that backwards and forwards, it will start to warm up and eventually break and deform. So that would be straining plastically. We go past the elastic limit into the area of permanent deformation, and some of that energy is going to be changed into heat because that energy has moved the atoms around permanently, so the material warms up a little bit. Okay, so you need the formula, and you need this understanding of some of the energy may be recovered and some will not be recovered if we get into the plastic region. Generally speaking, the calculations are pretty straightforward. This is a simplified version of the previous graph that we just looked at. Sometimes this you might see this, you just get a horizontal line instead of a curve. If you don't get that and you're asked to work out the area, then you might just have to estimate it, assume that it's a rectangle, or you may have to count squares, which is a bit more time consuming. But if you get something simplified like this, then it's pretty straightforward. So it says calculate the strain energy up to the elastic limit. Well, we know the elastic limit is the end of this constant gradient section. And strain energy, work done, basically the same thing. We just need to find the area of this triangle. So that's nice and easy. So it's half Fx, half base times height. So it's half multiplied by 20 mils. So watch out for that. Oh, sorry, half times 20 newtons multiplied by 5 millimeters. So this is a really important point. Always look at the units on the axes, because very often that might be kilonewtons or millimeters or something like that. And obviously we need to include that in our calculation, not just write down the numbers on the scale. So we have divided by 1,000 and we have 0.05. Part B, fairly similar. It says calculate the total work done in breaking the material. So we're assuming that at this point here it's going to break. Remember, normally this would be curved. This is a simplification. So all we need to do is to work out the total area of this trapezium. So you could do that in one calculation, but we've already worked out the area of the triangle. So all we need to do is to work out the area of this rectangle and then add that on. So we have 20 multiplied by 25 minus 5, which is 20 mils. And nice simple calculation, we have 0.45. So generally speaking, the calculations for work done and strain energy are fairly straightforward. Obviously, you need to practice how this applies to complex exam question scenarios, but the calculations generally are fairly straightforward. Right, we need to talk about the behaviour of polymeric materials. So we've already looked in lesson 1 at ductile materials and copper and metals. So if you get polymeric materials, that is rubber, so this is materials that are polymers, multi-chain molecules. If you do a similar practical where you, similar to the Hooke's law practical, where you get a rubber band and then you hang masses on it, but you don't test it to destruction, you just maybe go up to 1 kilogram, and then you start to unload them, then you'll get a different unloading curve. So this is quite unexpected, and it tells us something about what's going on with polymers and how they're structured. So we've got this curve here, which is not a straight line. Sometimes this is referred to as an S-shaped curve. Now, whether or not that is an S is highly debatable, but it's referred to as an S-shaped curve. And we actually have 3 sections. We have a steep section. This means that's a large spring constant. That means it's difficult to stretch. And then the gradient eases off a little bit, so the spring constant has reduced. And then it gets steep again, so it gets more difficult to stretch. So we'll talk about what the significance of this later on, but this is why we have steep, less steep, and then steep again. And we refer to it as an S-shaped curve. So generally speaking, it would not return to its original length, as in this case, which means it is inelastic. So we've defined elasticity, or elastic behavior, as returning to its original length when the load is removed. So this particular data here would refer to something which is inelastic. And we could also talk about the area underneath the line. We've already said that that represents the work done or the energy stored. So if I worked out the total area underneath the loading curve, ignoring the unloading curve for now, that would represent the work done stretching the rubber band. And then if I calculate the area underneath the unloading curve just on its own, that represents the area recovered that we get back. So as we take the masses off, it raises up vertically, so we gain back some GPE. But we don't go all the way back to the original length because it's inelastic. So there's a difference or a loss in energy, and that's represented by the area of this loop here. Sometimes this is referred to as hysteresis, but not all exam boards make reference to that term. So the area of this loop represents the energy lost, we know it's not really lost, converted into non-useful forms, in this case heat. So as we've mentioned previously, we talked about bending the paperclip. So this energy is used to permanently deform the rubber band at a molecular level. So yeah, this is we could talk about these 3 separate instances of area here. Okay, so why do we have this polymeric S-shaped curve? So long chain polymers are bundled up together initially. So all these long chain molecules are all kind of wrapped up, and there's a lot of attractive forces between those molecules because they're all bundled up. So to get it moving is quite difficult. So we have this steep section here. After that, the unraveling section of the change is relatively straightforward. So this middle section has a lower gradient because that bit is relatively easy. But then we get to the final stage where we have those polymers at full stretch, and then we're stretching them chains themselves. We're not just unraveling them, and we're trying to work against the atomic bonds within the molecule. So that becomes more difficult again. So we have, difficult to stretch, easy to stretch, and then difficult to stretch. This is why we get this particular S-shaped curve. Right, so relatively short video. So if you want to see the next video, we have material behaviour, which you'd need to check your specifications. So not all exam boards would look at that in detail, but you might want to check it out anyway. As ever, if you want a lot more detail, so if you want practice questions, exam questions, work solutions, quizzes and lots of other stuff, then go to payhip.com, grade A physics. I hope you enjoyed the video. See you next time.